Hi, everybody. Today in this screencast, I want to talk about potential energy as it applies to orbital dynamics. And I also want to talk about a concept called escape velocity, which is closely linked to black holes, which is something most of us find rather fascinating. Now, um, I just want to say that this topic can be a little bit challenging for students. And if you find it's causing you anxiety, just let it go. And here's why: the odds of you having this come up on the test are low. It does come up sometimes, but it's not going to be a big part of the test. So if you don't understand it, don't sweat it too much. And it's not going to be very heavily represented on your unit test either. But I do want to cover it. It's interesting stuff. So let's go. Okay, so we've talked about potential energy quite a bit in this course so far. And I've always said it's up to you to decide what to call zero. So look at the case here. I have three 1 kilogram masses. They're all basically the same height above the floor of the room. And I have a 1 meter high table in that room. So if that 1 kilogram mass is positioned 1 meter above that table, and I want to talk about how much potential energy it has, I would probably say, well, I'm going to set the table surface as zero potential energy and therefore say it has 10 joules of potential energy because it's 1 times 1 times gravitational field strength of 10. Okay. But if it wasn't over the table, if it was over the floor, then I'd say, nah, you know what? I'm going to make the floor my 0 point. So I'm going to say between here and here, it must have 20 joules of potential energy because it's 2 meters above the floor. But now the exact same mass at the exact same height above the floor, now it's on a pendulum that's swinging through its arc, and it's at the bottom of that swing, in which case I say, you know what? I'm just going to say this is zero potential energy because it makes it easier for me to understand the changing energy in this oscillating pendulum. The point is, when we allow ourselves to choose where to put the 0 point for potential energy, and make no mistake about it, on your AP test, you're going to have to do that. All right. But this is really what we call relative potential energy. And there's nothing wrong with that. But if you look at it and think about it for a second, there should be an absolute correct, like what, how much potential energy does it really have? And that's what we want to look at here. So in order to determine that, let's think of it this way: the absolute potential energy that an object can have is basically I have to figure out first, what is the maximum energy I can have by lifting this thing of mass little m away from a planet of mass big M, right? So there's a finite amount of energy you can get. Like, for instance, lifting a rock away from Earth is going to give more energy to the object than lifting it away from the moon. And so there should be a way of determining what is that absolute amount of potential energy that it can acquire. So think of it this way: if I take that 1 kilogram mass I was just talking about earlier, and I place it on, say, the floor of my room, I'm basically 1 r away from the center of the Earth, 1 Earth radii away, and therefore the gravitational field strength at this level of r is 10 newtons per kilogram, or 10 meters per second squared. So if I lift that object 1 meter, 1 kilogram lifted 1 meter against a gravitational field strength of 10, it acquired 10 joules of potential energy. But now, what if I instead started with that object being 10 Earth radii away? Well, remember that the gravitational field strength is inversely related to the square of the distance r. So since I'm 10 r away, I have 10 squared, or 100 times less gravitational field strength. So lifting at the exact same 1 meter of distance is going to acquire 1/100th the amount of energy. It only acquires 0.1 joules. So you can see, in just 10 Earth radii, I went from 10 joules to 0.1 joules. I'm dropping off pretty rapidly. So it turns out it won't be very much farther before it's not acquiring hardly any energy at all. So if we were to graph this, we get something that looks like this. Let's make this the force of gravity between a planetary object and a test mass. And let's make this the distance between the planet and the test mass. So what we see is, at first, a small change in distance. Well, first of all, let's just say this. This is what the graph would look like. Okay, it's an inverse square graph. And remember that energy is, or at least work, is a change in energy, and that's equal to force times time. And since this is force, did I just say force times time? I meant to say force times distance. I'm really sorry. And I don't want to go back and redo my screencast because I made one little slip. I'm not doing it. So I'm going to say it all over again and keep going. Let's try that again. So this graph here shows force versus distance, and work is force times distance. So if I multiply these together, I get the area under the curve. So in other words, if I integrate this, what I'm going to end up getting is the change in energy. The total amount of energy the object gets by being lifted against gravity, it can be found by finding the area under this curve. All right. And so basically, this is the maximum energy you can get. So if I have the object at this distance here, when I've essentially gotten to zero. Now I'm asymptotic to zero, but I'm really close to zero. If I move it further, it doesn't really acquire any more energy. So I can move it up, I can move it down, and it didn't change its energy in any appreciable way. Well, I say, well, that's what I should call zero. This should be zero. Now, what that means is anything closer would be less than zero. It would be negative. And that is something that bugs some people. So let's just look at why that is. So let's look at how we would calculate or derive an expression for the absolute value of UG. So let's think of it this way. We can find it by looking at how much work it takes to lift the object to that point we're just looking on the graph. So work equals force times distance. And in this case, the force is gravitational force, G M M over R squared. That's the definition of gravitational force, times the distance I've lifted, that's R. So if I just multiply these together, I lose one of these and I just get GMM over R rather than over R squared. So that's how much work it took to lift it. That's how much energy it acquired. So let's find what absolute is. So now we're just going to go to the conservation of energy equation, and I'm not going to leave off spring because it's not involved. So I'm going to say kinetic energy plus gravitational potential energy plus work initially here at ground level uh, is equal to the kinetic energy plus the potential energy that I end up with when I've lifted this object to whatever height I'm going to lift it to. Okay. Now keep this in mind. On the ground, it's not moving. It doesn't have any kinetic energy. It has some value for UG, an absolute value I want to find. Plus, I'm going to do some work. And in doing that work, I want to lift it to a height, but I don't want to have any kinetic energy. And at that height, I'm so far away, I'm going to say that at that height, it has zero potential energy at basically an infinite distance. So this equation just comes down to UG plus work is going to equal zero. And we just said work is equal to GMM over R. And so if I solve that for UG, I see I get negative GMM over R. And I know that I just point that because I know that negative bugged me when I first learned it. I didn't have it explained to me very well. That's why it's going to be negative because zero is at the far distance and anything closer is going to be a negative value then. So this is the formula for the absolute potential energy in terms of an astronomical object when we're looking at it actually in terms of the most it could have. So it's going to be negative GMM over R. Now let's talk about the kinetic energy of an object in orbit because this leads to an interesting idea, which is like how much energy does it take to move something out of orbit? Okay, so this is what the expression is, but I'm gonna derive it, then we're gonna talk about it. Okay, so basically, if you'll recall, the velocity of orbit is square root gm over r. Hopefully you remember that. If not, you should be able to drive it pretty easy using the centripetal force equation. I think we all remember that kinetic energy is 1/2 mv squared. So I'm just going to substitute this for v. All right. So when my velocity of orbit is this, so I'm just going to put in here see what I get. So the kinetic energy of orbit is going to be 1/2 m, and then the orbital velocity value squared. So this is what I get for the kinetic energy of an object in orbit. It's going to be 1/2 g mm over r. Okay. Look a little bit familiar. So now let's see what happens in terms of what we call binding energy. So think of it this way. The moon is gravitationally bound to Earth, right? It circles Earth. It never leaves Earth. So we say it's bound to us gravitationally. Now keep in mind, gravity never goes to zero. There's nowhere in the universe that you could go where the Earth isn't going to pull on you. And right now, you are gravitationally bound to the Earth. You're unlikely to ever be able to leave Earth. Its gravity won't allow it. But there is a certain amount of energy that I could add to you that would get you to where you leave Earth and you never come back. At that point, you're no longer gravitationally bound to Earth. It doesn't mean that the gravitational force isn't reaching you, but you're no longer bound to Earth. You're no longer doomed to spend the rest of your life on or orbiting Earth. Okay, so how much energy it takes to remove you from being bound to Earth is what we're going to call binding energy. And it's just kind of a fascinating thought that, people who work in NASA have to think about this. Okay. So let's just look at this. So we just said that this is what the kinetic energy of an object in orbit is. And we just said that this is what the expression is for the absolute gravitational potential energy of an object, in this case, an object in orbit. So if I want to express K in terms of UG, then what I find is this is positive 1/2, this is negative 1. So this is the negative 1/2 of this. And that's kind of weird to think about it, but if you sit down and look at it, it makes sense that K is negative 1/2 of this. So now I'm just saying mechanical energy of a satellite in orbit is simply the sum of its potential energy and its gravitational potential energy. So therefore, K is negative 1/2 UG, and UG is UG. So when I add them together, I find that the mechanical energy of orbit is 1/2 of this. That's pretty cool, okay? So if I then take this and write it out, well, what I get is since this is equal to this, the mechanical energy of an object in orbit is negative 1/2 of gmm over r. And the binding energy would be if I add this much energy to that object in orbit, then what happens is it no longer has any kinetic energy and it no longer has any gravitational potential energy. So it is no longer bound to the object it had been orbiting. So that's what binding energy means. If you add this much energy to an orbiting object, it's no longer gravitationally bound to that thing it had been orbiting. Now let's just talk about escape velocity. Okay, so escape velocity is related. All right, so let's think about this. Uh, escape velocity is essentially the minimum speed an object needs to have in order to become gravitationally unbound from the thing that it was orbiting. So remember that if the velocity of orbit equals the square root of gm over r, I have a perfectly circular orbit. And we said if you have less than that, you're going to have an elliptical orbit where this is r, right? So I end up closer to an ellipse where I end up closer to the star. And if the velocity is greater than this value, I end up with an ellipse where I end up farther away from it because I'm going faster. But it turns out if I go square root 2 faster than this value here, then I become gravitationally unbound and I drift away forever. So this value here is what we're going to call the escape velocity. So the escape velocity, oh, I thought it'd be this. So escape velocity is basically is square root 2gm over r. So if you have that speed, you never stop and come back the other way. All right. And it turns out at that speed, it doesn't matter which direction. If I sent you this direction or that direction or that direction, you're never coming back. So so you can think of it a couple ways. So escape velocity, another way, I think maybe even a more beneficial way of thinking of it is it's the fastest speed the object could have upon reaching the planet surface M uh, due to the gravitational interaction with the object. In other words, what's the maximum work that planet M can do on test mass little m? That's going to be your escape velocity. So in the case of Earth, that turns out to be how fast would that object be coming when it hit Earth? It would be going 11.2 kilometers per second. No matter how far you move an object away from Earth, the fastest the gravitational attraction between the Earth and that object can ever make it go is 11.2 kilometers per second. That gives it a certain amount of kinetic energy, which is equal to the absolute potential energy of the object at that height. So, since that's the escape velocity of Earth, what that means is if an object is launched away from Earth less than that, it will come back to Earth, or at least remain gravitationally bound to Earth. Maybe it will orbit Earth, but it will be gravitationally bound to Earth. If I launch it at more than that, and that's assuming I'm starting at distance r, then it's never coming back. It becomes gravitationally unbound. All right, so let's just see if we can figure out the escape velocity using conservation of mechanical energy. All right, so we're going to say that I start off with an object far, far away. Now, so I'm doing the opposite of what I did before. Now the object is infinitely far away. Okay, so at that point we say you have zero gravitational potential energy, and you have zero kinetic energy. Now, as that object moves towards the planet, this is going to acquire this. This is how much gravitational potential energy you have upon reaching the planet, and this is how much kinetic energy you would have upon reaching the planet. And so if I solve this, I end up getting, I can, because this is negative, I can put them equal to each other and say this equals this. And I'm just going to solve that for V, and I get escape velocity. So escape velocity is equal to the square root of 2gm over r. Pretty cool, right? Now, think about it this way. Why isn't there any air on the moon? Because if a molecule of oxygen or nitrogen was to touch the lunar surface, the molecular vibrations of the lunar surface, because of the temperature it's at by absorbing solar energy, is such that it would hit that object upwards. And as that moved up, it would leave the lunar surface with greater than this. And therefore, it becomes gravitationally unbound to the moon and it leaves it. But on Earth, escape velocity is significantly larger. Okay. And because it's significantly larger, then what happens is that same molecule trying to leave Earth does not have enough velocity to become gravitationally bound, and it's gravitationally bound to Earth, and it stays with us. Pretty cool stuff, right? Okay, now let's talk some really cool stuff. Let's talk black holes. Okay, I think most of us like this. So, uh, a, a black hole is basically formed when we have what's called a singularity. So, a singularity is this super dense, infinitely dense remnant of a collapsed star. So, basically, and a black hole is a region around that singularity, that dead star, that in which the escape velocity exceeds the speed of light. So here is a star that's alive, right? It's working. Okay, so it has nuclear fuel in here, and that nuclear fuel is pushing outwards. It's making hot gases want to expand. Gravity wants to pull it in, and it's in a state of equilibrium, like our sun is right now. But eventually, we'll run out of nuclear fuel, and the inside of that star will begin to cool off. And when that happens, it's no longer pushing outwards. So now gravity is going to start pulling this inwards. And as it does, it's going to become more and more dense. And if you look at the gravitational force equation, since it's related to the square of distance, if it gets half as big, the gravitational pull gets 4 times stronger, and these things get squeezed together. Now, what happens is, at first, we have what's called electron degeneracy pressure. The electrons don't, if you remember Pauli's exclusion principles from chemistry, electrons can't occupy the same quantum state. And so that creates this outward pressure. So in the case of the sun, it would actually stop when all the electrons are basically as close together as that would allow. But with stars that are larger than the sun, that is overcome. And so these electrons get squeezed together and they just basically move inwards. They join the protons, and the protons become neutrons. That was called a neutron star, which has incredibly high gravitational pull. But then I have neutron degeneracy pressure, which is keeping that from collapsing. Because the same rules basically apply with other fermions. But if I have basically, I think it's like two and a half. Maybe it's on my next slide. I forget. But if I have a little bit more mass than that, then even the neutron degeneracy pressure is overcome, and that whole thing just falls down into this infinitely dense point of matter that still has all the mass. It has all the gravitational pull, but just has zero volume. It's such a weird thing to think about. And so what would happen is as I approach that, R can get very small, and I get to a point where this right here is what would make the surface of the black hole. And the idea is, on this side of that boundary, and this boundary is called the event horizon, which I think is a cool name. On this side of the event horizon, the escape velocity is less than the speed of light. So if you shine light here, it can escape. But if you cross that event horizon, there's no way to become gravitationally unbound from this thing. So you are going to stay here. You're not getting out. Right. So black holes have this idea that things go into them, they don't come out because the escape velocity is greater than the speed of light, and you can't go faster than the speed of light. So if I want to find the radius of the black hole created by a collapsed star, here's what I need to do. I'd start with the escape velocity equation, square root 2 gm over r. I'd substitute the escape velocity for the speed of light, which we use the letter c, E equals mc squared. I'm going to put c here. So the speed of light equals this. And now I'm just going to solve this for r, and I get this. This would be the radius of a black hole. And listen, black holes deserve so much discussion. And if you want to know about them, take the astronomy class that Mr. Hopkins teaches, because you'll learn all about them. They are fascinating. Or talk to me about it. I love to talk about black holes, but I've spent enough time talking about it in the screencast. Anyway, and this screencast has gone on too long, and I'm sorry. So thank you for watching, if in fact you did, and I'll see you in class tomorrow.